Hey everyone, and welcome. Today we're going to dive into the physics of something you do literally all the time, seeing. We're going to explore ray optics and the incredible journey of light. Seriously, have you ever really stopped to think about it? When you look in the mirror, what's the actual physics going on that makes your reflection even possible? Well, that's the exact question we're going to answer today. So here's our roadmap. We'll kick things off with the basics of light. Then we'll look at how it travels and what happens when it interacts with different materials. After that, we'll get into the real magic of reflection and its unbreakable rules. And we'll wrap it all up with a pretty cool real-world application. Okay, let's start right at the beginning with the world of light. So to put it simply, optics is the part of physics that's completely obsessed with light. It's all about understanding how light behaves, how it moves, and how it interacts with, well, everything around us. Now here's where we get clever. Light is technically a wave, but when we're dealing with objects that are way, way bigger than its wavelength, like mirrors and lenses, we can simplify things. We can just treat light as a straight line, or a ray. This awesome simplification is the core of what we call geometrical optics, and it makes figuring all this stuff out so much easier. Okay, so we're thinking of light as a ray, but how does that ray actually travel through space? This is a big one, a core principle you absolutely have to know. It's called rectilinear propagation. It sounds fancy, but all it really means is that as long as the stuff light is traveling through is uniform, like clean air or still water, that light will travel in a perfectly straight line. It doesn't curve or bend on its own. You see this in action all the time. A beam of sunlight cutting through a dusty room, or the sharp, clean edges of a shadow. That's rectilinear propagation. It's proof that light travels in a straight path. But that straight journey gets way more interesting when light starts hitting different kinds of materials. So, let's explore how various media affect it. We can pretty much sort all materials into three groups. First, you have transparent ones, like clear glass or water, where light just sails right through. Then you have translucent materials, like frosted glass or cooking oil, where light can pass through, but it gets scattered and dimmed. And finally, you have opaque objects, like a block of wood or a piece of metal, which are basically a big stop sign for light. It can't get through it all. So what happens when light hits one of those opaque objects it can't pass through? That brings us to one of the most important concepts in optics, reflection. Reflection is exactly what it sounds like. It's the phenomenon of light bouncing back. When a light ray hits a surface, like the boundary between the air and a mirror, some of that light gets sent right back into the air. This simple principle is how mirrors work their magic. But wait, not all reflection is the same. On a super smooth surface like a mirror, you get what we call regular reflection. All the light rays bounce off at the same angle, creating a nice, clear image. But on a rough surface, like a piece of paper or the wall, you get diffuse reflection. Here, the light scatters in all directions. And this is so important. It's the very reason you can see objects that aren't shiny from any angle you look at them. Now, this whole bouncing back thing isn't just random. It follows two simple but absolutely unbreakable rules. And here they are. First, the incoming ray of light, the reflected ray, and the normal, which is just an imaginary line drawn at a right angle to the surface, all lie on the same flat plane. Second, and you'll want to star this one for your exams, the angle the light comes in at is always equal to the angle it reflects at. Angle I equals angle R. Always. This leads us to a really cool idea, real versus virtual space. Real space is our side of the mirror, where the light and the reflected rays actually exist. Virtual space is that world that appears to be behind the mirror. So your reflection is a virtual image because the light rays aren't actually coming from behind the mirror. Our brain just traces them back to that point, creating the illusion. Now that we've got the physics down, let's connect it to something you see every single day. Ever notice how many really important things are yellow? Think about it. School buses, taxis, streetlights. Why that specific color? Well, the answer isn't really about the light, it's about our eyes. The human eye just happens to be most sensitive to the yellow-green part of the light spectrum. That means we see yellow more brightly and more easily than we see other colors. So using yellow for things like school buses and streetlights is actually a safety feature, rooted directly in human biology and the physics of light. Pretty neat, huh? All right, let's do a quick recap of the key takeaways for any exams. Make sure you can define rectilinear propagation. You absolutely have to be able to state the two laws of reflection. You should know the difference between regular and diffuse reflection, and finally, be able to define the three types of media: transparent, translucent, and opaque. Nail those and you'll be in great shape. And this is why all of this matters so much. These simple rules, that light travels in straight lines and reflects in a predictable way, are the fundamental building blocks for everything from simple mirrors to massive, powerful telescopes. It really makes you wonder, how many other secrets of the universe are just waiting to be discovered, all by following a simple ray of light?